Welcome to lesson 6 on power system analysis. In this lesson, we are going to discuss transmission line capacitance, which we were discussing in lesson 5. We are continuing with it. Here what we will do is we will consider the effect of earth on transmission line capacitance. Actually, when we have these transmission lines, the phase conductors are in above the ground in overhead transmission system, and the distance between the phase conductors and the distance between phase conductor and ground are of the same magnitude, and therefore, the earth, which acts as a equipotential surface, does affect the electric field lines and thereby the capacitance. So, we need to consider the effect of earth in calculating the capacitance for transmission lines. So, in this lesson we will discuss how the earth or the ground affects the capacitance of a single phase transmission line and how it affects the 3-phase transmission line. Then we will talk about a double circuit line, and we will talk about how we calculate the series and shunt impedance of the double circuit line. In fact, when we have a double circuit line, the two circuits are somewhat close to each other, that is the 3-phase conductors of one circuit and the 3-phase conductors of the other circuit are most of the time placed on the same tower, and therefore, they are in quite close proximity, and because of which both the magnetic field lines as well as electric field lines do get affected by the currents flowing in the other circuit and the voltages present in the phase conductors in the other circuit. Therefore, for a double circuit line, we have the mutual effects because of the two circuits, and that needs to be considered, and we will see how we take care of this in this lesson. Well, we will first start with the effect of earth on transmission line capacitance. Now, as I said earlier, we consider the earth surface as an equipotential surface. Now, the earth surface may not be a plane, it may be undulating, it may not be horizontal, it may be inclined, but for our purpose of calculation, we will always consider the earth to be a horizontal plane surface. Now, if we see that there is a conductor as shown here, the phase conductor, which is charged with positive charge q per meter length, then the lines of electrical lines, field lines should be radiating from this in radial direction, but because the earth is acting as a equipotential surface, so these field lines will bend and go to the negative potential on the earth. So, the effect of earth is to change the configuration of the electric field lines, and thereby this will affect the capacitance of the conductor system. Now, how do we take care of this effect? Well, what we do is we use what we call as method of images. Now, in this, what we do is we consider a conductor directly below the overhead conductor, in the ground at a distance which is equal to the height of the conductor above the ground. That is, we are considering an image of this conductor below the ground. So, this is a mirror image of this conductor, and the charge on the image conductor is opposite of that of the overhead conductor. Now, if you see, if we have such a system, then the field lines will look like as shown here. Now, these field lines, if you see, are very much similar to if we had just this conductor and the ground in consideration. Therefore, what we find is that if we take another conductor with opposite charge and place it below the ground, just below the ground above below the ground of this conductor at a distance which is equal to the height of the conductor above the ground, then the field lines created are exactly same as that if this conductor is above the earth's surface. That is, the effect of earth can be taken care of by this kind of a situation. So, the method of images basically consists of considering image conductors below the ground at a depth equal to the height of the overhead conductor above the ground, and the charge on this image conductor is of the opposite polarity. So, if we do this, then we have a system which is consistent of the same effect as that of the earth. Now, we will try to use this for calculating the capacitance of a single phase line. So, capacitance of a single phase line considering the effect of earth. Now, here we have a single phase line with two conductors x and y placed at a distance d. The conductors have a radius of r x and r y. The charge on conductor x is q coulombs per meter and charge on conductor y is minus q coulombs per meter, because conductor y in a single phase system will be acting as a return conductor, that is, current flowing in x will be returning through conductor y. Now, this system of conductors, single phase two conductors, are above the ground at a height of h meters. So, if we have to now take the effect of ground or earth, then what we have to do is we have to consider image conductor x dash, which is placed directly below the conductor x at a distance equal to h below the ground. That is, the distance between conductor x and its image h x x will be equal to 2h, and the charge on this image conductor x dash will be minus q coulombs per meter. Similarly, we will consider the image conductor for conductor y as y dash, which will be placed directly below the conductor y at a distance of 2h, that is, at a distance h below the ground directly under conductor y, and the charge on this conductor y dash will be equal to plus q per coulomb per meter. So, now with this system we would like to find out the voltage between the two conductors x and y. We can write this voltage from the earlier lesson that we have had. We can write this voltage V x y is equal to q by twice pi epsilon into log n d y x, that is the distance of the conductor B to conductor A, divided by dxx, that is the distance of conductor A to conductor A, that is conductor x to conductor x. So, we in similar way we will write for the charge on conductor y. Considering the charge on conductor y, we will have the relationship q by twice pi epsilon minus q by twice pi epsilon d y y, that is the distance of conductor y to conductor y itself, divided by distance of conductor x from y. Now, due to the image conductor x dash, we will have the effect on the voltage given by q by minus q by twice pi epsilon log n h y x, that is distance of image conductor x to conductor y, and h x x, that is divided by h x x, that is the distance between x and the image conductor x. For the charge on the conductor y dash, we will have the term q by twice pi epsilon log n h y y divided by h x y. Now, if we consider all these terms together and arrange them, then we will get this as equal to q by twice pi epsilon log n dy x into dx y divided by dx x into dy y, that is this minus log n dy y by dx y can be written as plus log n dx y by dy y, and then we can add these two together. That will give me log n dy x into dx y divided by dx x into dy y. Similarly, considering these two conductors, this if we make it as negative, then this becomes h x y by h y y. So, this will be minus log n h x y by h y y. Therefore, if we add these two, then we will get minus log n h y x into h x y divided by h x x into h y y. Now, considering the symmetry of the figure that we have, h x x will be equal to h y y and h x y will be equal to h y x. Also, dx x is equal to r x and dy y is equal to r y, and if both the conductor have the same radius, then we will have that equal to r. Therefore, this can become as dy x and dx y are basically equal to d. So, this becomes q by twice pi epsilon log n d square by r square, which can be written as this square can be taken out. So, this will have 2 here and 2 will cancel with this 2. So, it will become q by pi epsilon log n d by r. In the similar way, h x y is equal to h y x. So, this becomes equal to h x y square, and h x x is equal to h y y, which is equal to h x x square. Therefore, this square term can be taken here. So, 2 will cancel with this 2 here. So, we get q by pi epsilon minus log n h x y by h x x. So, this way we have calculated the voltage between the two phase conductors x and y for a single phase line. Once we have got this voltage, we can calculate the line to line capacitance as C x y is equal to q by V x y. So, now this is simply q divided by Vxy that we have calculated. This will come out to be pi epsilon by log n d by r minus log n Hxy by Hxx farad per meter. Now, as we had seen earlier, the capacitance to neutral or capacitance to ground will be equal to twice Cxy, because the earth surface or the ground will have a potential which will be half that of between x and y. So, we can write Cn is equal to 2 Cxy, which is equal to twice pi epsilon log divided by log n d by r minus log n Hxy by Hxx. So, in this way we can calculate the capacitance considering the effect of ground. Now, here what we are finding that how this effect of ground is taken into account. If you see this expression and compare it with the expression for the single phase capacitance of a single phase transmission line, then we are seeing that it is this term which is an addition or for taking the effect of earth. And here we can see that if the conductors are very much above the ground compared to the distance between them, then dxy and dxx will be almost equal, that is, this distance and this distance will be almost equal if the conductors are very much above the ground, that is, h is very large, and in that case we find that the effect of ground will be negligible. So, if the conductors are not far off above the ground as compared to the distance between the phase conductors, then the earth does affect the capacitance, and the effect is in increasing the capacitance as compared to when we have not considered the effect of earth, because this total term is now getting reduced. Now, we will talk about the capacitance of three phase line considering the effect of earth. Now, here we have three conductors A, B and C placed at position 1, 2 and 3. The distance between these conductors are d12, which is the distance between A and B, d23, which is distance between B and C, and d31, which is distance between C and A. The conductors are carrying a charge of Qa. The phase A conductor has a charge Qa per meter, phase B conductor has charge Qb per meter, and phase C conductor has charge Qc per meter. Now, these conductors are placed above ground, and if we have to take into account the effect of ground, then we have to consider the image conductors. The image conductors will be for the phase A conductor here, which will be again at a distance which will be below the ground, which will be equal to the height of this conductor above the ground. So, this will be an image conductor here with a charge which will be negative of that of the conductor here. Similarly, for phase B conductor, we have our image conductor here with a charge minus Qb, and for phase conductor C, we have an image conductor with a charge minus Qc. Now, the distances from the phase conductors to the image conductors are given as from conductor A to its image A dash, it will be H11, that is considering this is position 1, Similarly, for phase A conductor and image of B, we will have the distance h12. For the distance from phase B conductor to image of A, it will be h21 and so on. So, we have all these distances which are shown in this figure. Now, we can calculate the voltage between two phase conductors. So, we will calculate the voltage VAB, the voltage between conductor A and B, and this will be given by 1 by twice pi epsilon into, due to charge on conductor A, that is QA, it will be log n D12 by R minus log n H12 by H11, that is log n D12 by R, that is from this conductor, distance of this from phase B conductor D12 and distance of this conductor from itself, that is D12, and divided by the distance from itself, that is D11, which is equal to R. So, we have this first term taking into account that part. Now, because of the image conductor that is placed here, again we will have minus QA is the charge on this conductor, and the distances from this to B will be H21 and distance of from this to A will be H11. Therefore, we have this minus log n, because minus QA is the charge. So, minus log n H12 by H11. Similarly, for charge on conductor B and its image, we will get the term 1 by twice pi epsilon QB log n R by D12 minus log n H22 by H12, plus due to the charge on conductor C and its image, we will have the term 1 by twice pi epsilon QC into log n D23 by D31 minus log n H23 by H31. So, just as we have calculated the voltage between the conductor A and B, we can also calculate in the same way the voltage between conductors A and C. So, we will get the voltage VAC in that case. If we add these two voltages VAB plus VAC, we had seen this is equal to 3 VAN. In this way, we can calculate the voltage VAN, that is voltage between phase A conductor and the ground or the neutral. And since we know the charge on conductor A as QA, therefore, we can calculate the capacitance Cn for or CAN for the conductor A, that is the capacitance for phase A conductor to ground will be coming out to be equal to twice pi epsilon divided by log n Deq by R minus log n cube root of H12 into H23 into H31 divided by cube root of H11 into H22 into H33. Now, here again what we are seeing is that the term log n cube root of H12 H23 H31 divided by cube root of H11 H22 H33 is the effect of earth on the capacitance. Now, this is getting subtracted in the denominator. So, the effect of ground when we consider for calculating the capacitance will be higher than if we neglect the effect of ground. Again, here we see if the conductors of the phase conductors A, B, C are very far above the ground compared to the distance between them, then H12, H23 and H31 will be very much nearly equal to H11, H22 and H33, and therefore, this term will come out to be 0, that is, the effect of ground will be negligible. However, since these distances between the phase conductors and the distance between phase conductor and the ground are of the same magnitude, the effect of ground is basically to increase the capacitance of the transmission line. Now, we will talk about 3-phase line with earth return. So, again we take into consideration a 3-phase system with neutral wires or the ground wires on top of the phase conductors. This is the configuration that we have for a 3-phase EHV system. Now, if the phase conductors are transposed, fully transposed and are carrying balance current, then there will be no current flowing in the earth conductors or in the ground. However, when there is unbalanced current flowing through the phase conductors, there is going to be some current which will be flowing in the earth conductors or the ground conductors and also in the ground itself. As we had seen earlier, we can take care of this by means of calculating the using the effect of images, as we had done for calculating inductance and calculating the resistance. So, here again, since these conductors are above the ground, what we are doing is we are considering the image conductors below the overhead conductors, again at a distance which is equal to the distance of the conductor above the ground. So, we are taking an image conductor and using the method of images. Now, we will have, instead of 3 conductors and n neutral conductors, we will have now 6 conductors and 2n neutral conductors in the system, because we have 3 plus n conductors for the neutral as the image conductors also. Now, for this system, again we can find out the voltage between any conductor and its image. That will be given by V k k dash. For any conductor k, we can write the voltage between the conductor k and its image k dash. That will be equal to 1 by twice by epsilon summation of m is equal to a to n n, where n n is the total number of conductors in the system, into q m, the charge on conductor m, log n, the distance from the image conductor m k to the mth conductor above the ground, divided by dkm, the distance between the kth conductor and the mth conductor, minus summation m is equal to a to n n, that is for all the conductors in the system, q m, the charge on mth conductor, into log n dkm by hkm, that is again the distance between the conductors, image conductor k to the conductor m, divided by distance between the conductor k and conductor m, divided by the distance between the kth conductor and the image conductor m. That is, this part is coming because of the image conductor m, this part is coming because of the overhead conductor M. So, because the image conductor carries a negative charge to that of the overhead conductor above, so this negative sign is coming here. So, if we add this, we will get this as equal to 2 by twice pi epsilon summation m is equal to a to n n q m log n h k m by d k m. That is, we can multiply it with by minus 1, then we can invert this. So, this will be plus sigma m is equal to a to n n q m log n h k m by d k m, and then we can add them. Now, the voltage between the kth conductor and the neutral or the earth will be equal to half of that between the conductor k and its image k dash. Therefore, V k n will be equal to half V k k dash, which will be equal to 1 by twice pi epsilon, because that 2 is cancelled out with this 2 here. So, it is 1 by twice pi epsilon summation m is equal to a to n n of q m log n h k m by d k m. Now, since the ground conductors, which are on top of the phase conductors, since they are grounded at regular intervals by means of tower footing, therefore, the voltage of these conductors with respect to neutral or ground is going to be 0, because these conductors are at ground potential. Therefore, V k n is equal to 0 for k is equal to n plus 1, n plus 2 up to n n. That is, except for the phase conductors, all these ground conductors, the n ground conductors, their voltage is going to be 0. Now, we can put this whole equation into a matrix form as shown here: V a n, V b n, V c n, and V n 1, V n 2 and up to V n n. These are zeros, is equal to a matrix of P's into Q a, the charge on conductor A, Q b, the charge on conductor B, Q c, the charge on conductor C, Q n 1 up to Q n n, the charge on neutral conductors or the ground conductors, which are placed above the phase conductors. That is, we are talking about the charges on these conductors n 1, n 2 up to n n. Now, here we see we can divide this P matrix, which will be 3 plus n n matrix, 3 plus n n by 3 plus n n matrix. This matrix we can divide into 4 submatrices P a, P b, P c and P d, where P a is a 3 by 3 matrix of which relates the voltage with respect to charge on the phase conductors. P b is going to be 3 by n matrix, P c is n rows and 3 column, that is n by 3 matrix, and P d is n rows and n column, that is n by n matrix for all the ground conductors. And see, P a is relating the phase conductors, P b is relating the phase conductors with the charges on the ground conductors, P c is relating the voltage on the neutral conductors with respect to the charges on the phase conductors, and P d is relating the voltage on the neutral conductors with respect to the charges on the neutral conductors. Here P k m, that is any of these terms P k, P a b, P b b or P n 1 b, any of these terms is given by the relationship 1 by twice by epsilon log n h k m by d k m meters per farad. Now, this matrix which we had, this big matrix relationship, can be written in a shorter form as V p, which is the voltage for the phase conductors, and 0, which is the voltage for all the n ground conductors, is equal to P a, P b, P c, P d, which we had already defined earlier, and Q p is the charges on the phase conductors, that is Q a, Q b, Q c, and Q n is the charges on the neutral conductors Q n 1, Q n 2 up to Q n n. Now, from this relationship we can write this as V p is equal to P a into Q p plus P b into Q n. Similarly, we can write 0 is equal to P c into Q p plus P d into Q n. So, 0 is equal to P c into Q p plus P d into Q n. This results into Q n is equal to, that is, we can take this part on the other side. So, this becomes minus P c Q p is equal to P d Q n, and again pre multiplying both sides by P d inverse, we will get Q n is equal to minus of P d inverse into P c into Q p. Now, if we substitute the value of Q n into this equation, then we will get V p is equal to P a minus P b into P d inverse P c into Q p. We can write this relationship as Q p is equal to C p into V p. We know the charge is product of capacitance and voltage. So, Q p will be equal to C p into V p, and where C p will be equal to the inverse of this term, that is inverse of P a minus P b P d inverse P c. Now, this C p will be a 3 by 3 matrix which relates the capacitances between the phases or the 3 phase conductors. Now, here what we have done by doing all this is we have eliminated the effect of the ground conductors, that is the ground currents which were flowing, that effect is included by modifying the phase conductor capacitances. So, C p is a 3 by 3 matrix, C a a the capacitance of A with respect to A, C a b the between the A and B, C a c between A and C. Similarly, C a b between A and B, C b b the capacitance between B and its image, C c c is between C b c between B and C, and so on. So, C p is giving us the capacitance for the 3 phase conductor system. Now, if the line is fully transposed, then we will have the same capacitances for all the 3 phase conductors as well as the same capacitance between the 2 phase conductors. So, phase to neutral capacitance as well as capacitance between 2 phases will be same for all the 3 conductors. Therefore, C a a hat is equal to CBB hat and will be equal to CCC. So, the 3 will have the same capacitance to neutral, whereas CAB and CBC will also be same. So, we are for a transposed line system, we are representing them with a hat, which shows that this line is a this capacitance is for the transposed line, not to confuse with the capacitance that we had calculated earlier. Now, the relationship which governs these capacitances CAA hat is the average of CAA, CBB and CCC, because each phase conductor is occupying the 3 positions for 1/3 length of the line. Similarly, CAB, which will be equal to CBC and CAC, for the transposed line, this CAB will be equal to 1/3 of CAB plus CBC plus CAC, that is the average value of the capacitance between the phases AB, BC and CA. Now, once we have calculated the capacitance, we can calculate the admittance very easily by just multiplying it by j omega. So, Yp or the admittance for the 3-phase system with ground wires will be given by this Yp, which is a 3/3 matrix. Again, this will have the terms j omega into Cp, which will be j into twice pi f Cp, where Cp again, as we have seen earlier, is a 3/3 matrix. Same thing will happen for the transposed line, that is Yp hat is equal to j omega Cp hat plus j into twice pi f Cp hat Siemens per meter. So, in this way we have seen that we can calculate the capacitance for any general system of 3-phase conductors, that is 3-phase conductors with any number of neutral wires or the ground wires on top of them. Next, we will talk about double circuit line. Now, in double circuit line, as we know, most of the time when the power demand to an area increases, we would use, instead of one circuit, 2 circuits, and both these circuits are running parallel to each other, mostly on the same tower. So, since these 2 circuits are running parallel to each other and are on the same tower, the distance between the conductors of the 2 circuit is not large. Because this distance is not large, the current flowing in them is going to affect the magnetic field of the current flowing in the other circuit. And similarly, also because the voltage of one circuit is going to produce electric field, which is going to affect the electric field produced by the voltages in the other circuit. That means there is mutual effect which takes place between these 2 circuits, because they are physically not very far off. So, they have effect from one on the other. Such a system we are showing here. Here we have a 3-phase line. This is one circuit and this is another circuit which is placed here. So, this is a double circuit system. Here we are showing this double circuit line. This is one circuit, this is another circuit connecting 2 bus bars or 2 substations. Now, the current flowing in one circuit is IP1, the current flowing in the other circuit is IP2, where IP is basically a 3 element vector which consists of IA, IB and IC. So, we have IA1, IB1, IC1 of the circuit 1 and IA2, IB2, IC2 for the circuit 2. Now, this current flowing here from one circuit will be IP1 plus IP2, which gets divided into IP1, IP2, and maybe it is getting connected on this side. This is the system that we are showing. We are talking about the effect of the two currents flowing in these two circuits, how they are going to affect the series impedance of the transmission line, as well as how they are going to affect the shunt admittance of the transmission system. So, first we will take up the series impedance. Now, for the two circuits we can write the relationship EP1 is equal to ZP1 into IP1 and EP2 is equal to ZP2 into IP2, but since these two circuits are close together, there is mutual coupling. So, it will not be right to write separate equations for the two. In fact, what we have here is we are considering a system of 6 conductors instead of 3 conductors. Again, since we see that these two circuits are connected on the two ends, so the voltage drop between them is going to be same. So, the voltage drop EP1 is same as EP2, which is equal to EP. So, we can write EP for circuit 1 and EP for circuit 2 is equal to ZP into IP for circuit 1 into IP for circuit 2, and ZP is going to be a 6 by 6 matrix of the series impedance. Now, from this relationship we can write IP1 IP2 is equal to ZP inverse into EP, because EP1 EP2 are same. So, we are writing EP for that. So, we are from here we are calculating this IP1 and IP2. So, we are pre-multiplying both sides by ZP inverse. So, we get IP1 IP2 is equal to ZP inverse EP. Now, ZP inverse will be admittance, and this will be again a 6 by 6 matrix, which we can divide into 4 submatrices YA, YB, YC, YD, where each of these submatrices are going to be a 3 by 3 matrix. So, this is equal to YA, YB, YC, YD, EP, and this is equal to YA into EP plus YB into EP. So, YA plus YB into EP and YC into EP plus YD into EP. So, YC plus YD into EP. So, now we can write, if we add the two currents IP1 and IP2, then we get IP1 plus IP2 is equal to YA plus YB plus YC plus YD into EP. That is, if we see from here, if we have IP1 is equal to YA plus YB into EP and IP2 is equal to YC plus YD into EP. So, if we add them, we are going to get this IP1 plus IP2 is equal to YA plus YB plus YC plus YD into EP, and this equation we can again solve for EP. Then EP will be equal to ZP dash into IP1 plus IP2, where ZP dash is nothing but the inverse of this matrix. Now, here if you look at this matrix, this is sum of this 3 by 3 matrix plus this 3 by 3 matrix. All these matrices are 3 by 3. So, ZP dash is going to be a 3 by 3 matrix. Okay. Now, we will talk about the shunt admittance for this double circuit line. Again, in the same way as we have done for a single circuit line, we can write down the relationship for QP for circuit 1 and QP for circuit 2, where QP will be the charges on phase conductors A, B and C. So, QP1 is QA1, QB1, QC1, QP2 is QA2, QB2 and QC2. So, this is a vector having 6 rows. Cp will be a 6 by 6 matrix, and Vp again is the voltage of the phase conductors A, B and C for circuit 1 and circuit 2. Since these two circuits are in parallel, therefore, the voltages are going to be same. Therefore, instead of Vp1 and Vp2, we are writing them as same as Vp and Vp. Now, this Cp, which is a 6 by 6 matrix, can be divided into 4 submatrices Ca, Cb, Cc, Cd. So, we have got Ca into Vp plus Cb into Vp. So, Ca plus Cb into Vp, Cc into Vp plus Cd into Vp, that is Cc plus Cd into Vp is equal to Qp1, Qp2. From here again we get Qp1 is equal to Ca plus Cb Vp, Qp2 is equal to Cc plus Cd into Vp. Therefore, if we add these two, we get Qp1 plus Qp2 is equal to Cp equivalent into Vp. Now, this Cp is going to be Cp equivalent is going to be a 3 by 3 matrix instead of a 6 by 6 matrix Cp. So, where Cp equivalent is nothing but equal to Ca plus Cb plus Cc plus Cd, and this is a 3 by 3 matrix, and therefore, we can get the shunt admittance for this double circuit line in terms of 3 phase system for which will give us a 3 by 3 matrix for the phase A, phase B and phase C, which includes the mutual effect between the two circuits. So, we will get Yp dash is equal to j omega c Peq. So, now that we have seen how to calculate the capacitance taking into account the effect of earth, and we have also seen how we can calculate the series or shunt admittance for a double circuit line taking into account the mutual effects. Well, let us take an example to illustrate some of the concepts that we learned today. We consider a 3 phase 400 kV 50 hertz 350 kilometer overhead transmission line with flat horizontal spacing with 3 identical conductors. The conductors have an outside diameter of 3.28 centimeter with 12 meter between the adjacent conductors. The conductors are placed 20 meter above the ground. We consider the earth plane to be a perfect conductor. Determine the capacitive admittance to neutral in Siemens per meter per phase and the capacitive VAR generated by the line. So, this is the problem that we have, and we can show this configuration graphically as shown here. We have the 3 conductors A, B and C placed here. We will say that these are positions 1, 2 and 3. There are 12 meters apart from each of the conductors. Since we are considering the ground to be a perfect conductor, we take the effect of image conductors. So, we have the image conductor of A as A dash, which is again 20 meters below the earth. Similar for B and C, and we have the distances h I j, which is showing the distance between the conductor I with the image conductor j. So, h13 is the distance between conductor A and the image of conductor C, and so on. So, we have seen that H11, H22, H33 is the distance between the conductors and their mirror images, that is H11, sorry, this should be H11 from this conductor to this A to A dash is the distance between image conductor. This will be 40 meters. Similarly, B dash will be 40 meter and C dash will be 40 meters. So, and Hij, as we have said, is the distance shown in the figure. Now, we have for such a system, following the same procedure as we have shown earlier, that is, if we go back here, we have the capacitance to neutral for 3-phase system with image conductors. This is given by this relationship. We write the same relationship here. So, we have C n is equal to twice pi by epsilon divided by log n dEq by r minus log n H1 H2 H12 H23 H31 divided by H11 H22 H33, a cube root of that. So, now what we do is we substitute all the values. We can calculate dEq as 15.119 meter, which is basically the cube root of the distance between the conductors themselves. R is the radius of the conductor, which is equal to 1.64. It is 3.28 divided by 2. From the diagram, we have the values for H11, H22, H33 as 40 meters, H12, H23 as shown here is equal to 41.761 meters, H31 is equal to 46.648 meters. Now, putting these values in the equations, we get C n is equal to 8.2595 into 10 to the power minus 6 microfarad per meter. Hence, we can calculate the admittance Y n is equal to twice pi f, which is 50, into the C, this is C n, that is 8.2595 into 10 to the power minus 12 Siemens per meter per phase. This is equal to 2.595 into 10 to the power minus 9 Siemens per phase. Now, length of the line is given as 350 kilometers. Therefore, total admittance will be simply multiply this by 350, this comes out to be 908 microsiemens per phase. Now, the war generated by the line QC will be equal to Y n into VLL square, or QC is equal to 908 into 10 to the power minus 6 into 400 into 10 to the power minus 3 square, that is 400 into 10 to the power minus 10 to the power 3 into 400 into 10 to the power 3, this is 400 kilovolts. So, this comes out to be 145.358 MVAR. So, that is all discuss about the capacitance calculation. In the next class on lesson 7, we will discuss about modeling of transmission lines. Once that we have learnt about how to calculate the parameters of the transmission line, that is the resistance, the inductance and the capacitance for the transmission line. Now, we would like to model the transmission line for analysis. So, that we will do in lesson 7. Thank you.